So you should all be here, I guess. There shouldn't really be any latecomers, because I guess you should have all been here for the last hour or so. So what I'll do is I'll kick off exactly on time. So I'll just leave it 2 minutes, let these people come back from the loo, and then we'll kick off. And for those of you on your laptops, I've just put on the Moodle these notes. I've just actually finished adapting them. So if you want to get the latest version, it's there. So I got two main comments from so I closed the SET survey, the Student Evaluation of Teaching survey, just now, and to look at the results. And the results have gone over 30%, so the survey now counts, which is excellent. Overall, it was people seem to think it's all right, this module, and my teaching of it. There were two main comments that came out. People wanted the full block of notes, like every single slide in front of them, rather than the mini handouts. Who would like that? Who would actually like the whole set of notes printed? Would you actually really like that? Okay, who doesn't care? Yeah, okay. I might go back to printing them. I just think it's such a waste of paper in this digital age, where the stacks of notes I get in my office are like that much for each lecture. So I will think about going back to printing them all. The other comment was me moaning at people telling them to be quiet. Well, I think I told you in the first lecture that I just can't focus when people are talking. It's just absolutely cannot focus, and can't give a lecture if people are talking. So that's it. Sorry, it's just me. That's it. Right, so I'll give it another 30 seconds, and we'll kick off. Well, I think there's a grammar mistake on the first slide. That's not very good. All right, so it's 11 o'clock. Let's go. So this lecture's got two parts to it. The first part is about transistors, and I was thinking that I don't think I go into enough depth about transistors generally. So I spent quite a lot of time this morning actually rearranging these slides to try and expand or put in more detail what you know in better context about transistors. And the result is, after this lecture, you're going to be able to know basically a few useful transistor circuits that you'll be able to use yourself in your projects. So I thought that'd be pretty handy. And then, how many of you were at the examples class where we did Boolean algebra? How many of you, hands up, who was at the examples class? Who doesn't know what I'm talking about? A few hands. Okay, so you weren't at the examples class. So I'm going to go over Boolean algebra again at the end of this lecture, just to make sure that we've all got it. Yes. It can be a revision for those of you who are in the examples class. So here's an overview of today's lecture. Firstly, I thought I'd talk to you about the transistor as an amplifier. So last lecture we did transistors, last lecture we did computers, but before that we did transistors as switches, which are sort of on, off. But this one we'll look at them as an amplifier in their transistor state, and I'll talk to you about that. Then we'll look at some simple circuits, so a security light circuit, a Darlington pair, and then we'll move on to Boolean algebra. So we looked at this relay example a couple of lectures ago, which I said relays are a bit like transistors, and they're sort of just a big mechanical switch that works by effectively having a magnetic field, and it just sort of pulls a switch shut. So, and the result is you can use this relay to turn on very, very big motors, high-power motors, with very, very low voltages and currents. Now, I then said, we can use a transistor for that, and transistors are really, really cheap, they're really small, and they don't draw much power. So in sort of portable devices, you want to be using transistors to switch things on and off rather than relays. They've also got lots of other advantages, like they're quick, transistors are mechanical devices, therefore slow, etc., etc. And we basically learned that if you put current into the base of a transistor, so I've got a mouse, so I've got a mouse instead of a laser. So if you put current in the base of the transistor there, it effectively turns on this big current at the right-hand side, and your light bulb lights. So this is sort of an amplifying circuit in that you can use a very, very small current going into the base to make a big current, or to use a big current to drive a light bulb. And those of you who are in that lab, or went to the labs, would have seen my fantastic art of this Transistor Man cartoon. So this is actually after, it's called Howitz and Hill. So if you want a really good practical book on electronics, it's about that thick, fantastic book, get the book Howitz and Hill. And in that book, they draw this cartoon in a little bit of a better fashion. And the idea of this cartoon is effectively, you can think of a transistor, so this black device with 3 legs, as effectively there's a man in there, and he's looking at the base current. So he's looking at this very small current that's going in the base of the transistor. So I'll just show you where the base is. So that's this base current here that the man's looking at. And he's constantly looking at this current flowing into this base. And depending where that dial on the meter reads, he adjusts his big valve to let in more current or let in less current. And we can think of that pipe's the base, that pipe, the input to that pipe's the collector, and this output's the emitter. So we've got these 3 cases. We've got no current going into the transistor, so and the transistor's off. We've got a bit of current going into the transistor, and the transistor's a bit on. And we've got a lot of current going into the base. We've got a lot of current flowing from the collector to the emitter. Now, the interesting thing about transistors is their name. So if you think about the name of transistor, it says it's called a transresistor, if you sort of say it in a very long way, transresistor. And what this sort of means is a changing resistance. And previously, we've looked at the case where a transistor was 0 ohms, so switched on, or a mega ohm, or some really, really big value, so switched off. But this state where it's got a state where it's sort of a bit on or a bit off. So, you know, it might have a resistance of a few ohms or a few kilo ohms. This sort of intermediate state where it's sort of this transresistance period is very useful for building things like amplifier circuits and all types of electronic devices that we'll look at now. So in that state, it can be used as an amplifier. So you can write a bit of mathematics. So the mathematics in this lecture doesn't get more complicated than this. So you can write so who recognizes that from the lab? Do you recognize this from the labs? Yeah. So this formula basically gives you the gain of a transistor. So how much gain will that transistor give me? So if I put 1 electron into that base, how many electrons will I get flowing between the collector and the emitter? And you can see it's called beta. So beta is the gain. It's like the magnifying factor from the current flowing through that collector, or when we put a small current in the base, so IB, how much bigger will that current be that's flowing through the collector? And that's called beta. Of the transistors you measured in your labs, I think beta was maybe 200, maybe, something like that. So that's typical value of beta, about 200. So that's a bit of maths. Now, I'm now going to teach you about a bad security light circuit. So this is sort of a relatively basic circuit that you can build with a transistor. I'm going to show you how to build it badly, and then we'll correct it later. So before I can tell you about that, I need to tell you about light-dependent resistors. Now, these are quite fun devices if you get them. You get them in lots of sort of kiddies' electronic kits, so those 2001 kits where you wire things together. And what it is basically is it's just a resistor, and it's really, really tiny. It's just a resistor, and it reacts to light. So when you shine light on it, its resistance goes to 0 ohms, basically, or very, very low. And when it's in the dark, its resistance goes up to maybe a few, I don't know, a mega ohm or something like that, a lot of ohms. And these things are used everywhere. They're used in security lights to only turn the light on when it's dark, and all types of things. You can wire it into, I don't know, like little robots so it can detect where the light is and follow the light. They're very fun devices. And you can look at the characteristics of this curve. So at the bottom, I've plotted light intensity, so 0.1 lux to 1,000 lux, which is sort of dark to bright sunlight. And up the left-hand side, I've plotted the resistance of this device. And this is sort of a cartoon, but generally speaking, the resistance looks like this. So in the dark, it's about, get a bit over a mega ohm, and in the light, you get a very, very low resistance, a few ohms. So this is the typical characteristic curve for a device like that. Now what we can do is we can, on that there, the bottom, can you see this little square in the round circle? That's the symbol for your light-dependent resistor. What we can do is we can wire this light-dependent resistor into a little transistor circuit, and we can use it to sort of make a security light circuit, so our light will go on when it's dark. So you might have this at home for your porch light or something. So in darkness, our light-dependent resistor is going to have a resistance, a big resistance. In this case, I'll say a megaohm, a big value, okay? So we can calculate the voltage at point V1 in the circuit there, so I'll just highlight point V1. So there's V1, highlight point V1. So we can calculate the voltage in the dark at point V1. So we've got a 20 volt supply up there, and it's just a potential divider circuit. So we've got 1 megaohm, which is the resistance of that LDR, divided by 1 megaohm plus, I've just put a 10K resistor there. So everybody shout out what the voltage at V1 is going to be? 1 over 1 times 20? 20, right? So it's just a simple potential divider, and we get the voltage at V1 is 20 volts. And if you notice, we've got 20 volts effectively into our little transistor. So the transistor is going to go on, transistor goes on, and the light switches on. So we've made a circuit that turns the light on in the dark. So when the resistance of our LDR goes high, the potential V1 goes high, and then the light goes on. All good. Let's look at the case in the dark. So we've got 10K, so we've got another potential divider circuit. So this time we've got 0 ohms. I've just called it 0 to make the maths easy. 0 ohms for our LDR sensor, divided by a megaohm plus 0 ohms. So we've got 20 over a million. So that's going to be a very, very small value. So V1 is basically going to be 0. And the transistor turns off and our light's off. So our light only goes on in the dark. That's quite handy. And I'm going to show you the problem with this circuit. So the problem with our circuit is that it's basically, this LDR turns on and off very slowly, okay? It's not a sharp on-off. So when it's very dark, it's got a very low resistance, it's got a very high resistance, and when it's very light, it's got a very low resistance. But in between, it's got this sort of on and off phase. So, when it's sort of midday or, a bit dark in the evening, it's going to have a resistance somewhere between the minimum and the maximum. And, this resistance will just vary as a function of light intensity. So you can see, as the day goes on, it gets darker, the LDR's resistance is going to, as the day is going to get higher. And what this means is, if you think about our circuit, our light bulb is never going to be on or off. It's going to be a bit on, or as it gets darker, the light will get a bit brighter. And that's fairly a useless circuit because your bulb's going to always be on, and it'll break and use lots of electricity. If you think about your sort of lights, your security lights at home, they aren't on all the time and adjust their brightness depending on how bright the sun shines on them. They're either on at night or off. So what we need to improve this circuit is sort of a more rapid turn on and turn off. Now what we can do is use something called a Darlington pair, which was invented in Bell Labs in, I think, 1953. So all a Darlington pair is, basically, is 2 transistors back to back. So what you can see happening is exactly the same circuit as before. So it's exactly the same circuit before. But you can see the current from our sort of sensing side of the circuit is going to the base of this transistor. And this will obviously amplify it because we know transistors amplify stuff. But then what happens is this current from this transistor goes out again into the base of another transistor, and we know transistors amplify stuff, so it's going to get double amplified. And this is called a Darlington pair. And what this means is, and you can buy them, by the way, this is sort of the top of a Darlington pair, you can buy them just in package. You don't actually need 2 transistors. And if we look at the gain of this, I'm not going to prove this, but you can there's no point in proving it, but if you look at the gain of this double amplifier, so this one transistor after the other transistor, the overall gain is one beta times the other beta. So in effect, so if we've got one transistor with beta 1, and we've got one transistor with beta 2, beta total is beta 1 times beta 2. And what this means is you can sort of cascade two transistors like this to give you a bigger gain and more amplification, so you get a higher overall beta. And what this means is you only need a very, very, very small amount of current going to the base of the first transistor to really turn the circuit on. So it turns on much, much more quickly, and it'll turn off much, much more quickly. So this is the actual circuit that's used in things like security lights. Now then, I'm going to show you some sort of simple circuits now that use this Darlington pair, because it's quite a handy circuit. I'm only really telling you about things that I think are actually genuinely useful and I've used in my career. So that's push-pull pair. That's genuinely a useful circuit. This Darlington pair is a genuinely useful circuit. This isn't just some theoretical concept to make your life difficult. So here's an application of a Darlington pair. And this time we're using it in a timer, okay? So this is a timer circuit, so we can make events happen. You might want to do this with mechatronics. You might want you might want to push a button, and then the device might want to wait before it switches on, and then runs off or whatever. So this is a simple timer circuit. And the way it works is the following. You see we've replaced our LDR with a capacitor there. This is how it works. So you push the switch, so you put your finger on the switch, and what this does is it basically shorts out the capacitor and discharges the capacitor. And it brings this point V1 right down to 0 volts. So the transistor's off, okay? Transistor's off. You've shorted out the charge in the capacitor, no charge in the capacitor, transistor's off. Then, what happens is charge flows through this resistor into the capacitor, okay? So the voltage on the capacitor builds up and builds up and builds up and builds up. And after a time, it'll reach 20 volts, okay? And you can look at so there's the build-up of the voltage on the transistor, and I've just written a bit of maths with a tau. And have we got a pen? So the time constant, so like this, can you see that tau in that formula there? The time constant in any RC circuit, so if you've got, the time it'll take any resistor and capacitor, so there's a battery, to charge, is always tau equals RC. That's always the time it takes capacitor, resistor to charge. That's sort of the time constant. And it always fits in that equation there. And you can see, as time goes on, your voltage ramps up. And at some point, what will happen, at some point what will happen is this voltage, V1, will go over the point to turn on your Darlington pair. And all of a sudden, your light bulb will light. I don't know if I've got an animation of that. I haven't got an animation of that. Your light bulb will light. So this is sort of a simple timing circuit, effectively. Now, you can't time very long events with this for two reasons, or one reason. So, it wouldn't be a very good alarm clock circuit, because these capacitors, or the longer you want your time to be, the bigger the capacity you want. So if you wanted to time something for an hour, you probably need a good size, expensive capacitor. And the other problem with this circuit is that if you want the time period to be very, very, very long, what you've got to do is increase R, so make R massive, so current flows into the capacitor really, really slowly, and increase C. Now, to have a big C, you need an electrolytic capacitor. And electrolytic capacitors are sort of can-shaped capacitors you might see if you look at electronic devices. And they have a leakage current. So when you put charge into an electrolytic capacitor, some charge leaks out. So at some point, your leakage charge sort of through the capacitor is going to get bigger than the charge you're charging it with. So the whole thing just won't time anything. It just won't never switch on. So it's quite a good circuit for mechatronics and things like that. But I wouldn't use it to rely on to wake up for an exam. So that's the Darlington pair. I've taught it to you because it's sort of a useful circuit, and I think you should know about it. Any questions about it? Any burning questions? Nope. Okay, good. So I thought now I'll just tell you about a transistor oscillator. So if you're electronic engineering students, I would now dive off into oscillating circuits, and we'd do like analysis of circuits like this for ages and ages. But all I thought I'd say is that you can use transistors to make signals turn on, off, on, off, on, off. And this can be useful for lots of things, like modulating light and transmitting information. It's a very, very useful thing to be able to do. And I just want you to know, basically, that you can, if you make a circuit with 4 resistors and 2 capacitors, you can make a signal that goes on, off, on, off, on, off. And it's incredibly useful. And again, by tuning the value of the resistors and the capacitors, just like we did with the previous circuit, we can change the time period of that pulse. Now, I'm not suggesting you go and do that or buy that, but if you do want to make pulses like that, you can buy chips like that called the 555 timer chip, which is a very, very famous chip. And there's much better chips than that will make these signals for you. So I just want you to be aware that transistors are, and these sort of, I want you to be aware of this sort of class of circuit. Okay, now, we're going to move on to Boolean algebra. This is going to be like a recap of Boolean algebra. Any questions about transistors before we leave the topic totally? Okay. Nope. Well, that's it for transistors from me. Boolean algebra. So this is going to be a refresher for those of you who are in the examples class. So here's an AND gate, and we know all about the logic to an AND gate. We know that it only goes on when you put in a 1 and a 1, and it goes off for every other situation. So this burglar alarm will only sound when we put in a 1 and a 1. Okay? And there's the truth table. The same with the OR gate. We know the truth table for an OR gate. We know that the output to an OR gate will go on when either of the inputs are put in. So if you put in any 1 into A or B, then the output will go high. And it'll only be off when both inputs are 0. And we also know about NOT gate. We know that the output of a NOT gate only goes high when the input is 0. So it's sort of this inverting gate. And there's the truth table again. So this is revision. Now, Boolean algebra. You can describe this whole class of circuits using mathematics. And this is quite handy because you can write expressions for whole networks of gates using mathematics, basically. So you can describe AND gates, OR gates, NOT gates, XOR gates, NAND gates, all with like an algebraic expression. And this is incredibly handy for describing logic and manipulating it. So if you want to write the mathematical expression, or the Boolean algebra expression for an OR gate, it's this. So if you want to represent this in maths, you go A plus B equals Q. Now, in Boolean algebra, this plus is not a plus like in mathematics. It's not like add. It doesn't mean add. The answer coming out of an OR gate will never be 2. It's only going to be 1 or 0. So what this plus means is OR. So it means A or B equals Q. Okay? So if A and B are 1, so 1 or 1 equals 1. Okay? It's not going to be 2. So here's the truth table. So 1 or 0 is 0, 1 or 1 is 1, 1 or 0 is 1, 1. So it's the only time when 1 plus 1 equals 1 in your whole life. 1 or 1 is 1. Okay? So it's like the OR gate represented as this mathematical expression. Now then. And we can expand it. So we can do sort of multiple OR gates with lots of gates. So now we've got at the bottom 1 or 1 or 1 equals 1. Okay? And there's the algebraic expression. The other sign we've got is a dot. So this represents the symbol for an AND. So here's our AND gate, and I've written this Boolean expression for an AND gate. So it's A and B equals Q, or A dot B equals Q. So here's the truth table for our AND gate, and I think I'll write it out again in full. Yeah, so 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Never think, when you're doing Boolean algebra, never think multiply or add, because you'll get yourself into a huge sort of confusion. Always remember, dot or star or whatever is always and plus is always or. And we can write the expressions for quite complicated circuits like this. This, in fact, very complicated circuit. So here I've got, to kick off, 2 OR gates with inputs A, B, C, and D, with intermediate values of A and B, and an output of Q. And we've got an AND gate at the back end. So let's firstly write the Boolean expression. So if we want to, we're now going to derive a Boolean expression for this whole circuit. So if we want to calculate an expression, or write an expression for that intermediate value of little a, what we can write is little a equals a or b. Just write it down. Easy. Okay. Now we can look at the next OR gate. So intermediate value of b, so this value of b here, is equal to c or d. So we've got the expression for b. It's this easy. It's not difficult. Now, what we can do is we can write an expression for the output stage. So we've got little a and little b going to an AND gate. So we've got little a and little b going to this AND gate. Gives us q. So you can write q equals a and b, right? So the next stage is to get an expression of the whole circuit is substitute those values in. So we can substitute little a and little b into q equals a and b, and we get this expression that just looks like one of those polynomial expressions you expand at school. And that's the expression for this whole circuit. Okay. Do I expand it more? Yeah, and what you can also do is you can just apply normal algebraic rules here. So you can expand this out. So if we've got q equals a plus b c plus d, you can expand this out. So you can get a and c plus a and c plus b and c plus b and d. And then you could actually just go ahead. So exactly. And if you had some letters that were the same, for example, two A's here, you could go ahead and simplify the expression. So it's just like, it's got most of the rules of the same algebra you had at school, but just be aware that pluses are ors and ands and dots are ands. So let's look at another circuit. Let's look at this circuit. So again, so this time we've got two ands on the input and one or on the output. So again, write the first expression for this AND gate. So we go big A and B, and together equals little a. Write the expression for the next gate. And we can go, the output of the next gate is equal to C and D. And then again, we can just write, we know this in OR gate, so we can just write the expression for all these values added together. Okay? So I'd like you to have a go at evaluating these expressions. So come up with the answers for these 5 ones here, and we've got the constants a equals 1, b equals 0, c equals 1, and d equals 1. So just have a scribble at that on paper. Yeah. And if you get the answer 2, you're wrong. So I'll just wander around, see how you're doing. So I want the values of q basically for all of these. Just have a go. You should be able to do it in your head, actually, most people. You done it? You got 2? Good. Go on, just have a little scribble. You all got it in this row? Yeah, it's not too tricky, is it? I'll give you all another 30 seconds or so. You should just be able to get the answer out. So there's actually, I think, one of the example sheets, there's quite a lot of this Boolean algebra in it. I think a few lectures back. And I suggest you have a practice. And you'll find loads of examples on the internet, and you'll get, so there's loads of examples of this. You got it? What have we got? Yeah, okay. I think we've all got it, pretty much. One man scribbling at the front. But, yeah, so that's basically Boolean algebra. It's not difficult. It's pretty handy. Yeah, okay. So the only other thing I've got to tell you about is this this bar. So you can when you look at data sheets, you'll often see something like a bar as an input to a chip, or if they're really lazy, what they'll put is a slash like that because they can't be bothered to write the bar symbol. What this means is not. Okay, this means this is a not operation. So you might see something like, so if you've got a chip here, you've got a pin, you might see something like reset bar. And what this means is that if you put a 0 on the reset pin, it'll reset the chip. But if you put a 1, it won't reset it. So you often see that looking at data sheets. So, yeah, and again, 0 bar is 1 and 1 bar is 0 because it's the inverse. Okay. And then, hang on, I don't know what's coming next. Yeah, so we've got a little circuit for an OR gate here, and if we put a NOT gate on its input, we can just write A, NOT, or B, and that's the expression for it. Okay, so it just means invert. Little rule, not very tricky. And again, if we invert the second input, we can write A NOT plus B NOT. Okay. So have a go at these expressions now. So, or draw out the following circuits for these diagrams. So these have got some knots in them, so just have a go at that. Just have a little doodle. First one's really easy. How are you doing? So just doodle them out. There we go. Doodle out the circuit. What have we got here? How are we doing here? What's the first one? Okay. What have we got here? Yeah, first one's right. Good stuff. First one's right. What's we got here? How are we doing? What have we got? Yeah. Okay. How are we doing here? Okay, got on to the second one. Very good, very good. Just have a little doodle. You got them here? How are you doing? You're doing it in your head? That's very good. Okay. Okay. Oh, you got them all there, I think. Got a lot of them. Who wants more time to doodle those out? Who wants more time? I'll give you more time. Who wants no time to doodle them out? Who's had enough of doodling? One hand. Have you done them all? No. Okay. So I'll show you the answers. Right. So am I going to show the answers? I'll draw out the answers. Or shall I draw out the answers? I'll draw out the answers to a couple. So the first one's really easy. A bar is just a NOT gate. NOT gate. Let's do the next one. The second last one is just an AND gate. So there's a big AND gate with 4 inputs, a NOT on 2 of them. There you go. Okay? So that's it. It's not hard. Right. Now then, that is the end of my talk material, okay? So you might have noticed this lecture was a bit sort of, had various things. So what I'm now going to do is I will repeat or go through anything anybody wants. If there's any topics anybody wants to repeat, I'm very happy to, I've got all the slides here on Moodle, and I will go through any difficult topics you don't like. So if there's anything you want, shout out now, okay? And if not, I'm very happy to answer individual questions that you may have. Tomorrow's example class is going to be exams, as Arthur said. So we're just going to go through past exam papers. So you know, if you bring questions about electronic exams, we'll go through them. Okay. So any particular wishes for material to be repeated? So we can vote. Basic logic, shaft encoders. So just put your hand up if you really want me to go through it. Understanding digital circuits, latches, shift registers. Shift registers? No. Shift registers easy. Basic op amps, summing and inverting amplifiers. Accelerometers and strain gauges, I'll go through any of that. One hand, so you're winning at the moment. Diodes, solar cells, rectifiers. 2, 3, 4, you're outvoted by a factor of, so your wish comes second now. Transistors, BJT suite, I think we've done transistors to death. And go through MOSFETs, principle of MOSFETs. Analog to digital, digital to analog. Microprocessors. This slide. No. Okay. So, surprisingly, we'll go through diodes, solar cells, and rectifiers. Is there any particular part of that you'd like me to go through? What do you find most difficult? I'll tell you what, I'll get the slide deck up, and then okay, so we've got the, So we've got introduction to diodes, power supply is the basics, designing a power supply, the bridge between AC and DC, the less ideal diode, and other kinds of diodes, including solar cells. What would you like me to go through? Shout. Who voted for this? What would you like me to go through? Okay, so the people who voted, would you like me to go through power diodes, the basics, designing a power supply, the diodes, the bridge between AC and DC, so that was bridge rectifiers. 1. Okay, so you win so far. The less ideal diode, so that was with the resistors and things like that, or solar cells. So solar cells, you want solar cells. 2 for solar cells, right. Okay, so I'm afraid you're outvoted. We'll come back to yours in a minute. See, I thought all that would be hard. Right. So, solar cells. Now then, to understand solar cells, you've got to understand diodes. Now, this may be the hard bit. So the thing about diodes is they're made from 2 types of material, N and P type material. Now, these materials have negative charges in them and positive charges in them. So they've got negative charges on the left, positive charges on the right. So we've got red and green. Now, the thing about charge that you may have learnt at school, but I'm not sure. The thing about charge is when you have lots of charge, it produces a voltage. Okay, so if you have like, if you run up and down the carpet and you charge yourself with static electricity, and you go to your friend's ear and touch your friend's ear, your friend gets a massive electric shock, and that's because there's this relationship called Gauss's law. That's basically a relationship between charge that's around and voltage. And because our diode is full of charge, you always get across it 0.3 or 0.8 volts. So whether this thing's just sat around, just in the drawer, or, anywhere, it's going to have 0.3 to 0.8 volts across it. And you actually measure this with a voltmeter. And this is called a built-in potential, and it's very, very useful. Whoops, wrong computer. It's very, very useful because you can think of this 0.8 or 0.3 volts as a little battery in your diode, okay? It's producing always a little voltage across your diode. So here's a model of our diode. So we've got, on the left-hand side, basically, an ideal diode. So this is a perfect diode. This diode will either be, so here's an IV curve, a diode. So in negative voltage here, and here's positive voltage. Negative voltage, our diode will be off. And as soon as we have a positive voltage, it goes on. So we can get infinite current through it. However, it's an object, so it's like a thing, so it's got some resistance to it. So we won't have a curve that goes straight up because it's got some resistance. We'll have a curve with a bit of a line. And if you go V over I on this line, you'll get R, so the resistance of the diode. But we've also got this battery thing, which is representing this built-in voltage of the diode. And what this will do is it'll shift this curve. It'll shift this curve along a bit, so it'll need about 0.8 volts to turn on. So that's how you come across this ideal diode curve. So this is sort of the less ideal diode curve. Now then, so there we go. There's our ideal diode, non-ideal diode, and then with this built-in battery thing. So now we understand this concept as sort of little built-in potential voltage in our diode. We can go and look at solar cells. So there we go. So if we imagine our diode as a box with a little built-in voltage across it, so 0.6 volts, positive on the left, negative on the left, and we stick some photons in, so we have some photons coming from the sun, these photons are going to generate charge. It's going to generate positive charge and negative charge. So they're going to generate, your photons are going to generate a positive charge and negative charge. And this is the thing about solar cells, because they've got this built-in potential, they've always got this voltage across them, this voltage is going to pull positive charge to one contact and negative charge to the other contact. So it's actually going to sort of split up that charge, and you're going to get current flowing out of your diode. Now what happens is if we put in a load of photons, so millions of photons, we're going to get loads of charge generated, and this charge will be pulled to the contact by this voltage. And because it's got to the contacts, it's just going to be spat out the end of the diode, and your solar cell will start generating electricity. So this current will appear, this charge will appear as current on the output of the diode. And then we can do some calculations, and I've got you to do some calculations. And the thing is, the only difference between a normal diode, so something you use for power electronics, which looks like that one up the left, and a solar cell, is some clever manufacturer's got the diode and sort of spread it out to be a nice big thick, a nice big sort of wide panel so it can absorb lots of photons. And the things that sort of affect how much current you get out of a solar cell or power is effectively this built-in voltage that you have between one contact and the other of your diode or your solar cell, and the number of photons it absorbs, so you can increase the number of photons it absorbs by increasing the area and make it better. So that's sort of the sketched example, or how solar cells work in a very quick cartoon fashion. Did that answer the questions, the guys who put your hands up? Does that do the trick? Okay. Do you want me to do rectifiers now? Yeah? Okay. So actually, I thought this bridge rectifiers, was the most complicated topic. So I'm surprised only a couple of people want it. Did you want rectifiers too over there? What did you want? Yeah. Okay. And? Yeah, you do anyway? Okay, great. So I'll just go through power supplies in general. So I've got 10 minutes. I can teach you power supplies in 10 minutes. Not a problem. Right. So if you want to run computers, things like that, AC will turn them on and off 100 times a second. This is bad. You get unhappy chips. For happy chips, you need a nice, steady DC voltage. So you need something to make the AC go to a DC, right? Now, the easiest way to do this is with a single diode. And if you get off eBay some $2.99 death trap mobile phone charger, it'll have a circuit in it just like this. And it's terrible, basically. What it does is it's got one diode, and it effectively just lets through the positive parts of the sine wave. And what you can do, and it's still an unhappy chip because we've got this voltage going on, off, on, off, on, off. This is bad. Stop me at any point, you guys, if you want me to. Stop. So a much better circuit is this bridge rectifier. And this is a really clever circuit, and you can buy them in little packages, like you can buy little 4 diodes in a bridge rectifier package, and they look like a little square black thing. And this is how it works. So watch the sine wave on the bottom left. So this is the voltage that's coming into it. So you put a positive voltage in. I'll do it with the mouse rather than my hand. Current flows through this diode. So you see this diode's blocking it here. It can't get through here. Flows through here, along here, down this resistor, to here, down here, and out here. So we've got current flowing this way through our load. Now, the input voltage goes negative, so we now have current flowing along here. It's being blocked by this diode, can't go down there, along there, down through our load, to here, back out along here. And we still have current going this way, so the same way through our load. So we've always got current going one way through our load. And then we can repeat the cycle, so current's flowing all the same way through our load, flip the AC signal again, and current flows the same way through the circuit. So it's sort of a trick way of making always current flow through your load out the same way, no matter which way the input's applied to the circuit. Does that make sense? Yeah, that makes sense? Okay. So that's all very good. So no matter what happens on the left-hand side, we always get current flowing through the load one way. And the result is we have sort of a bumpy, looks like lots of hills, voltage applied over our load. And our chip's semi-happy. It's not super unhappy. So to sort of smooth this out, all we do is we slap in a capacitor. So here we've slapped in a capacitor. And what this capacitor effectively does is sort of store current whilst your supply is switched off and give it back to the circuit when your supply is switched on. So we'll just go through that very briefly. So basically, when you've got, here's the sine wave again. When you've got a big voltage here, the capacitor sucks in all the charge it can get from the supply. And then what happens as your supply voltage goes off, so here it is going off, here's the supply's off, your capacitor is now in a position to basically give back this charge to your load. So it always makes sure your device has got some power, whether it's coming off the mains or off the capacitor. And you can see as the capacitor discharges, the voltage of the capacitor drops, and so the voltage being supplied to your device will also drop. What else? Yeah, also notice this capacitor can't supply current back to the mains because it's being blocked by these two diodes here. Okay? And the process continues. So it charges when there's power available from the mains, and discharges when there's no power available. Yeah, and the bad thing about this is you get this ripple. So computers don't like ripple at all. And also, the mains is totally variable, so it's not always totally steady. So it's never 240 volts, absolutely bang on. It goes up and down. And also, the shape of the sine wave also changes. So an ideal sine wave might look like that in my world. But if you've got lots of these power supply circuits with capacitors, so you can see that capacitor is always filling itself up at maximum, like peak of the sinusoid. If you actually look at the mains voltage, because of all these capacitors sucking current at the top of the mains, it actually reduces the shape of the mains and makes it look more like sort of square. So actually, plugging things actually changes the shape of the mains. So you've really got no control over what that ripple voltage is going to look like, depending on who's running a motor or whatever next to you. So to sort that out, what you do is you pop in some type of voltage regulator circuit. And what this voltage regulator does is it effectively eats up any ripple and just makes sure you get a nice steady DC voltage. Does that answer your questions? Yeah? Anything else? Is that all right? Okay. What was it you wanted? Strain gauge stuff. Okay, that's quite a big topic for 4 minutes. I'll try. We've got 4. Could this be it? I don't know if this is it, actually. I think this is probably it. Yeah, I didn't give this lecture. This was after I was somewhere else. So what would you like me to tell you about strain gauges? How they measure the strain? Oh, I can do that. Easy peasy. I can do that in 4 minutes. Right. How do they measure the strain? Oh, by the way, books. Books. This book, don't like it very much, but it's okay. This book on the left, brilliant for digital electronics. Book on the right, fantastic for op-amps and transistors, really, really meaty. Get it if you start getting well into this topic, but you don't need it. You don't need this book. Book on the left's quite handy, maybe a bit handy. Book on the right's really, really good, but really very, very meaty. That book, fantastic. If you can get it for like 30 quid off Amazon, get it. It's brilliant. Right, how do they work? How do strain gauges work? Basically, they're made of quartz. It's just quartz, like quartz you dig out of the ground or see where you go hiking. And the thing about quartz is it's got this lattice. So I don't know if in school you've looked at crystalline lattices and you have these sort of positive and negative ions like in salt. Well, here's what I've drawn for quartz. The structure's a bit different, but anyway, I've drawn that. And what happens is when you squeeze quartz, what happens is you deform this lattice, you deform this crystalline lattice. And if you see in the first picture, if you look at that one, all the charges are like perfectly balanced out, like it's totally symmetrical, and it's sort of at a neutral state. But by squishing it with your hands or whatever, you sort of deform this lattice and it's no longer neutral. But to make the whole thing overall charge neutral, charge starts appearing at the contacts. So like the crystal's trying to balance out its total charge to make itself zero charge. And to do that, the charge appears on the surfaces. It's a sort of a reaction to deforming its perfect crystalline lattice. And this charge can be measured. And what we can do is we can slap a massive weight on top of our quartz crystal. And because we know F equals ma, right? So when we get acceleration, this mass is going to press down on our crystal and it's going to squish it and produce charge. So there we go. We've got a bit of F equals ma, making some charge on the side of our quartz crystal. We can slap on an ammeter to our quartz crystal and measure this charge that's coming off it. But this charge is really, really tiny. It's like really difficult to measure, super difficult. And there's an actual accelerometer that looks a bit like a bolt. Okay? Now, the thing with this is very small charge, so we need an op-amp to amplify it. The other thing about this is the current is not actually proportional to the force you're applying. The relationship between current and force is a little bit complicated. So let me go through this. So you can think of this quartz crystal with a charge on the contacts, a bit like a capacitor, okay? Because it's got two metal plates on the quartz, a bit like a capacitor. Everything's a bit like a capacitor in these lectures. And we know the charge coming out of a capacitor, I, equals dq by dt, okay? So when you charge the plates of a capacitor, you know the current coming out of it is equal to dq by dt. So we can say the force that or the charge that we put on the plates of our quartz crystal is proportional to the force. So therefore we can say the force or the current that's coming out of our piezoelectric crystal is proportional to the derivative of the force with respect to time. Yeah? And we know F equals ma, so we can go the current coming out of our crystal is going to be proportional to dA by dt with respect to m. So the current is actually a measure of change of acceleration with respect to time, right? But that's a bit of a weird quantity, change of acceleration with respect to time, because it's not acceleration. It's like the derivative of acceleration, which is not useful, really. So what we do is we solve this problem by integrating. So if we just integrate that expression on both sides, we get integral of I with respect to t is proportional to a. Okay, so if we integrate the current with respect to time, we get the acceleration. And then Arthur introduced this nice integrating circuit, which all it does basically is store in that capacitor all the charge that's shoved into it, and then the output voltage, V out, is proportional to the current that's come into it. So this is like an integrating circuit. So I'll skip forward a bit. So if we slap our accelerometer on the left-hand side, voltage out is proportional to acceleration, and then what we can do is we actually cascade these integrating units. So if we want to get acceleration, we just use 1. If we want to get acceleration integrated, which is velocity, we use 2. If we want distance, we use 3 to get acceleration integrated twice. Happy? Better? Okay. That's it. So, yeah, examples class tomorrow. We'll do exam papers, exam questions you asked for. And then next week, I think Monday we're off because it's a holiday. And I think Thursday there'll probably be more quick questions like this, or some type of help class, maybe. Okay. All right. Have a nice week, everybody.